If you take a look at number 1, we're given the acceleration of an airplane, the time it takes for it to accelerate down the runway. We can assume that the initial velocity is 0 because the plane is presumably starting from rest. So, taking into consideration the variables that we have, we can use the d equals vt plus 1/2 at squared equation. The first term, the velocity initial times time, cancels out because the initial velocity is 0. So then plugging in for the rest, we can solve for distance. In the third question, we're dropping a feather. And it's important to remember that when you drop something, you are starting with an initial velocity of 0. We're given the distance that it falls, the acceleration on the moon. So we can take a look at our formula for distance, and again the first term cancels out because we do not have an initial velocity. So we can plug in the rest. I'll rearrange and solve for t here, and then we get the time it takes for the feather to fall from the moon. In question 5, we have again the acceleration of an aircraft, the final velocity required for takeoff. We can assume that the initial velocity is 0. So our VF squared equation is convenient here. Let me rearrange and solve for displacement. And now we have everything that we need. In number 7, we have an initial velocity, and then we slow down and come to a complete stop, so we know that the final velocity is 0. We're given the acceleration. Don't forget we're slowing down, so it's negative. So it looks like our VF squared equation is going to be the best in this case because what we want is displacement. So let me rearrange to solve for displacement, and then we just plug in our numbers, and we are on our way. In number 9, we are looking for the distance. We're given initial velocity, we're given the total time, which is 12 minutes, and we're given the acceleration. So I'm just going to solve this in one fell swoop here. We can use our equation for displacement. Notice how I'm using 12 for time in both cases. I'm not using the 10 for the first part and the 2 for the second part. I need to use the entire time throughout, 12 minutes in both cases that the t appears in the formula. And let me show you on the next slide exactly why I did that. Let's graph it. Let's graph velocity versus time for this one. I know that I'm going to be starting at 0.5, so that's why I put that up on the velocity. I put my 10 and 12 there for time. Now check out the formula. D equals vt plus 1/2 at squared. That first term, the vt, is kind of like what I've just drawn in yellow. The velocity is 0.5, the time is 12, 0.5 times 12, it makes a nice rectangle on our vt graph there. Remember, distance is the area under the curve of a vt graph. So the area of that rectangle is essentially the velocity times the time. Let me show you here with my pink marker. That term refers to the area of that rectangle. Now, the second term refers to the area of that triangle there, because at 10 seconds we start accelerating to 0, and so as I graph that, I see it makes a triangle. So let's look at the formula again. Let's look at our real numbers and see if you can see how it matches up to the graph. So as we go along here, we're taking our total displacement if we had no acceleration whatsoever, that's the 0.5 times 12, and then we're subtracting from it our slowing down portion. So we're taking an entire rectangle and then we're subtracting out the triangle part that we don't need, which represents the acceleration. If we were speeding up, then the triangle would be sitting on top of the rectangle and we would be adding it. But because we're slowing down, we are subtracting it. Alright, I hope this was helpful.